Hey folks, so I'm going to do a quick simulation slash demo slash victory lap uh, to show off my section of the code for this project. So first I'm just going to do a quick little demo, just like run the code, show you what the outputs look like and stuff. And I'll go through the actual text of the code itself. So first of all, I did a cute little startup thing. Panopticon is a word that sounds cool, and the little transition there is supposed to be like the transformation that the code does to the images. I thought that leaving the eye in the center would be spooky, which is obviously really good. So the first thing it does is it tries to calibrate the pixel distance. So like how far a distance in real space each pixel of the image counts for. The idea is that the workspace is going to look kind of like this, where there's like a pink background or maybe like bright red or bright blue, and then there's going to be like a series of dashes along one of the edges. In this, it's the dashes are black, but as long as they contrast with both the background and the wreath, I think it should be viable. Each dash is supposed to be like a set number of inches long, and then there's the same number of inches until the next one. And then it just keeps going like that all the way down the side of the field of view. So since that screen was empty, it didn't find any wreaths, so it just says on the console, no wreath detected. In this one, there's a little bit of a wreath, just kind of poking in from the side. We still don't want to start tracking that because, we want to make sure that there is in fact a wreath coming, and that's not just like, the top of somebody's head entering the field of view or whatever. So it prints out the field of view is still empty. For this one, it's far enough in that it's going to start tracking the wreath. So it tells us the wreath was found. It gives us the current position based on the this right here, the edge between an empty column and a column with stuff in it. It also gives us the previous position, which in this case is just the edge of the screen. But in future iterations of this loop that we're going through, it'll start tracking. It's going to keep the present position it just found, and send it to the next iteration, basically. And that also gives us instantaneous velocity and average velocity. And average velocity right now I'm calculating off of the most recent 20 measurements. In the actual application, it should probably be over the last second or two. However, many samples that ends up being depending on the FPS we're taking pictures at. So that just kind of keeps doing that. You can see that just the way that I have this set up right now, the apple ends up looking like the background, which I thought is kind of funny. So anyway, now we're starting to get to a point where there's two wreaths on the screen. It starts checking for wreaths from the left-hand side. So whichever edge comes up first, checking from the left, is the one that it records. And right here, we have a situation where the wreath that we'd been tracking this whole time is starting to leave the work area. So the position measurement we're going to get off of this image is actually from this edge over here. And since there's like a little branch in the code there, it lets us know that it's tracking a new wreath, and it doesn't calculate velocity based off of that measurement. So it also starts keeping a tally of the positions of whichever wreaths are between the edge of the field of view and the work area. and I just set that to 60 because it turns out to be a nice number for this simulation. But obviously that'll be like an actual distance, presumably in inches, between wherever like the physical edge of the field of view is and the start of the work area is. And that's something we'll measure once we get on site and start setting stuff up. So from here I just start repeating the same set of images we just mashed through. Just the way that the algorithm works, it wouldn't pick up any more of this wreath. It's just going to start tracking this one forever at this point, even if I had left the other one in. So we can keep mashing through this. We get a new wreath. It starts tracking two at once. Oh, I don't know if I mentioned, but it's subtracting the average velocity from every wreath in the queue there, so that we know based on the average like where everything is. Alright, so now we got a flag triggered that says wreath entering the work area. And we can tell that this first one that we'd been tracking has now gone below 0. And then it just kind of keeps going like that. And that's pretty much the gist of the program so far. Alright, so basically to start going through the code itself, this monstrosity is just a series of file names that are all of the images that it's going through. And it's stored in something called a deck, which is a data type I didn't know existed until I started writing this program. But it ended up coming in a lot handy. And it's not doing anything in particular right here, just I don't have to count all of the elements in that array. It can just tell me. So we're setting Festive Boy, which is our main image, to whichever image is in the array next, or in the deck next. Eventually it'll start reading images in from the flycap camera, or the black fly camera rather. But just for this, I just have like a folder with a bunch of these images. Then next we have op array, which is what we're doing all the operations to. It's the same size as Festive Boy, but it's only in black and white. It has the type CVU8, which is it's like 8-bit unsigned char or something like that. Basically, it just stores everything as 0 to 255. Next, we have our current position and our previous position both get initialized to all the way on the right-hand side of the image. We have the two decks that we're actually using for real purposes, the velocities and the timers. Timers is actually just like the positions of everything, but we decided to call it timers for whatever reason. Next we have our flags. So we have RHS check. So that's the thing that the flag gets thrown if it can't find a wreath. So then it starts trying to make sure that it starts checking like way the hell over on the right hand side to see how far a wreath is into the field of view. Next we have the flag separation anxiety, which triggers when a wreath leaves the field of view. And lastly we have the flag lacquer ready, which is just it's just like a stand-in basically for whatever information we send to the control system stuff. So here's our cute little startup image thing. If space becomes a concern, this is the first thing to go. I just think it's neat. Next we have our section on calibrating the pixel distance. It'll return a -1 if the calibration failed. But aside from that, it'll end up being whatever value the function kicks back. It's possible that PPI could end up being a negative number, at which point we want to make it a positive number, which is what this little bit here does. So next we're going into the main control loop. It starts by clearing the flags in case they were triggered on the last one. We're not clearing RHS check because that's one that has to persist between iterations. P-current gets set to -1 if there wasn't a wreath in the previous iteration. So if that happens, we want to make sure that p-previous gets set to festiveboy.columns, which is all the way on the right-hand side of the screen. If we leave it at -1, or if we allow p-previous to get assigned -1 in this next segment here, then I'll really screw up a lot of the math, and it doesn't like this very much. But otherwise, yeah, we just assign p-previous to whatever the current image or the current edge was in the last iteration. So next we take a look at our new image that we're just getting it from the deck up top, but it'll be from the camera in the full version, I guess. We do a function called thresh_RGB, which sets up and then runs the OpenCV function in range. And what that does is it sets everything between two thresholds to white in terms of like two thresholds of RGB values to white, and then everything else is black. So basically I just estimated the colors that a wreath would end up being. So anything that's like fairly green gets set to white, and then like the background gets set to black. So next we have a little bit here where if the right hand side check flag was set to true on the last iteration, then we do wreath detect. If that returns true this time, then we clear RHS check and we keep going in the program. Otherwise, we just keep going. So if RHS check was set to false on the previous one, or it wasn't cleared right up top, right before this, then we can, or sorry, if RHS check is clear, either because we found a wreath last time or we found a wreath this time, then we update p-current to be equal to whatever gets kicked out of our edge detect function, which we'll go over later. But basically, it looks for a column that is all black, followed by a column that is it has some amount of white in it. And p-current gets set to, or edge detect returns -1 if it can find an edge. So basically, if we get a -1 out of that, then we'll set the RHS check flag and skip a whole bunch of code. Otherwise, we check to see if, well, this expression, basically if we switch from, so like in that case where one of the wreaths was starting to leave the field of view and there is still another one in there, we'll get a previous measurement that's like really close to 0 and a current measurement that is like much closer to the right hand side of the field of view. So basically this is checking to see if the difference between these, it's checking to see if the current measurement is greater than the previous measurement by more than 1/5 of the width of the screen. Because if that's true, then presumably we're looking at a new wreath. In that case, we flag separation anxiety, and we skip a part of code. Otherwise, if it looks like both of the measurements are from the same wreath, then we can calculate velocity and This is called velocity calc, but it's actually doing both current velocity and average velocity. But yeah, so it does that, and then we trigger or don't trigger Lacquer-Ready based on what the return from timer calc is. And again, we'll go into what the functions actually do in a second. But basically, it'll return a Boolean where if it looks like a wreath has entered the work area based on, the average velocities and, all the other wreaths that we've seen leave the field of view, then it'll set to true. And then if it looks like they're all still not entering the work area, then it sets to false. And then it just adds another line here at the end, and then it goes back to the start of that loop. And it keeps doing that until it runs out of images. In the full version, when we're actually using camera input, it'll probably go until it can't find an image. I know that there's like a OpenCV thing where you can say like if the image is empty or whatever. So anyway, now we're getting to the functions, which is the noodly bit. So first up is thresh-RGB, which again, it's just to set up an in-range call, basically. It just takes our festive boy mat as mat in, it takes the opera mat as mat out. It defines two scalars for the upper and lower bounds for what's going to be turned to white in the opera, and then it runs the in-range function, and then it goes back. Next we have edge detect. So basically how this works is, and I'm not sure if this is like a particularly efficient way of doing it or whatever, but basically it goes through each column and sums the values of all the pixels in the first column and all the pixels in the next column. And if there's a wreath, it'll look like the current column will be 0 and the next column will not be 0 because there'll be like one white pixel in it or something. And in that case, it returns whichever column that was that it just found it in. Otherwise, it returns a -1. Next, we have wreath detect, which uses a pretty similar system. So basically, it just determines the right-handmost 10% of the image. This is an int, and I'm multiplying it by a decimal value, which the system really hates. Since I'm using like a really low resolution image for testing, this ends up giving me something that's actually pretty far off what it's supposed to be. But in an image that's, what, like 1024 by 720 or whatever the resolution of the camera ends up being, like a fraction of a pixel one way or the other, just it doesn't matter. The point is that we're looking at the right-handmost 10% of the screen. But so it starts at the right-handmost 10% of the screen and just sums every column until it hits the edge of the screen, and it increments our counter full columns if there was a column with some white in it, basically. And then because we're dividing integers, we have to do this pretty wonky calculation in order to get a good value. Next up we have the velocity calculation thingy. So this one uses the deck data type, and basically what a deck is an array that has dynamic size, and you can add stuff to the front or the back, or remove stuff from the front or the back whenever you want. So we're using this to basically only be checking the most recent however many number of velocity values, and then we can get rid of ones that are from a while ago without a hassle, and we can add in the new ones that we're just taking now without having to shift a million values around and stuff like that. So right now I have the max size being 20, but it'll probably be significantly larger than that in the full version. But if the size of the deck is higher than 20 or equal to 20, then it kicks out whichever one is in the front, which I believe should be the one that was taken furthest, longest to go. Yeah, the furthest amount of time in the past. I'm bad at speaking. But basically, so each time it gets called, it pushes to the back of the queue the new velocity calculation based off the two positions, the current position and the previous position, and it multiplies it by the pixel distance. And then to get the average, we sum all the values in the deck and then divide by the deck size. And that's what we return to get average velocity. Next we have timer calc. Again, we're calling it a timer, but it's just a series of distances that we're keeping track of. This one also uses a deck to keep up with the all the timers that we're tracking. The idea is that we can get rid of timers that have already expired and keep adding new ones as they leave the field of view. So each time separation anxiety gets flagged, we'll add a new timer to the back of the deck with frame distance as the value, which is, again, is the distance between the edge of the field of view and the work area. And then this is just for like feedback to the console, basically. If it's empty, then it just starts printing wreaths. And that's what this is too. Or no, that's what this is. But this part is it's subtracting the average velocity from every single timer in the deck. And then over here, we check all the timers, and then if any of them are less than or equal to 0, that means that they're entering the work area, so we kick them out of the deck, and then we trigger flags and whatever. So we return true if we just kicked one out, and we return false otherwise. So the last function is calibrate PPI, which calibrates the pixels per inch. So it starts out by doing the thresh RGB thing again. So we set up our scalars up here, and then we do in range. And this time what we're doing is we're assuming that the dashes are black and the background is not black. So by doing in range, we turn all the black things in the image white, and all the white things in the image, or I guess everything else in the image, we turn everything else black. So next up, we do sort of the same thing as in edge detect, where we're just doing all the columns again until we find one that has a sum that isn't 0 followed by one that is 0. Also, we're only checking the bottom half so that we don't accidentally look at like any hooks hanging into the field of view. But basically, we're just looking for the edge of that tape, the edge of the dashes. So next, if there wasn't a, if we couldn't find a tape, or if we couldn't find the dashes or whatever, then we exit the function and return a -1. Then the last part is where we're doing edge detection again. We're just looking for like the top of a dash and the bottom of a dash. It doesn't matter which order we find them in, as long as like the dashes and the space between dashes are all the same length. But given that, it'll be able to find the top and bottom, subtract the two to get a distance.